The Harbour Bridge has become world famous as a symbol of Sydney, but its construction was the result of over 100 years of discussion and planning. Work finally began on the bridge in September 1926, after consideration of several designs, following the tender of the English company Dorman Long and Company Limited. This photograph, taken in 1926, shows the Dawes Point pylon at an early stage of construction. In the background is the southern approach to the bridge. By the middle of 1927, construction of the approach trusses was well advanced. The curved northern approach viaduct would soon reach the Milsons Point pylon. Dr. J.J.C. Bradfield, the engineer-in-chief, had originally planned to use a cantilever bridge, but the long straight portion on the north side meant a very sharp curve towards Milsons Point station. The change to an arch bridge allowed a flatter and longer curve to begin at the northern shoreline. By 1928, the approaches were complete. The pylons had reached deck level, and construction had begun on the creeper cranes to be used on the arch. Fabrication of the steelwork took place in the workshops at Milsons Point, where Luna Park and the North Sydney Olympic Pool now stand. Erection of the main bridge started in late 1928. This photo, taken in early 1929, shows the southern cantilever 2 panels out from its pinned base, as well as some of the anchor cables sloping from the top of the main truss over the top of the pylon. The cables were attached by temporary joints to the ends of the main trusses and looped through tunnels cut deep into the rock behind the pylons. The number of cables was progressively increased as the cantilevered main trusses stretched further over the harbour. Construction on the northern side, on the right in this photo, was kept 7 months behind the southern side. The main reason was that if any problems were encountered on the southern side, steps could be taken to remedy them on the northern side. As a result, work on the northern side always proceeded more rapidly than on the southern side. By 1930, the 2 halves of the arch were only a few panels apart. At this time, Henry Mallard, a Sydney photographer and sales manager for Harrington's photo store, sought permission to film the construction of the bridge. Dr. Bradfield refused for safety reasons, but Lawrence Ennis, the director of construction, gave Mallard permission and allowed him access to all parts of the bridge. Over the next 2 years, Mallard visited the site regularly, taking hundreds of photographs, as well as shooting movie film with the newly developed compact camera, shown here in his left hand. For many years, a copy of the resulting film was held by the Institution of Engineers, and in 1969 it was viewed by Frank Litchfield, then aged 80, who had been a supervising engineer during the construction of the bridge. As he watched the film, he provided the commentary which is used throughout this program. Although many Australians, especially Sydney-siders, believe the Sydney Harbour Bridge to be the largest arch bridge in the world, this was never so. 4 months before Sydney's bridge was opened, the Bayonne Arch near New York was completed. 25 inches, a mere 635 millimetres longer between the base pins.
That shows the up through the throat of the arch with the sway bracing. Those 3-inch cables were used to crisscrossing of a tension with hydraulic jacks to give rigidity to the structure as it was built out. Well, just when we'd reached the construction and got out to the 14th panel with the crane on the 13th panel, the deflection of the half cantilever were about in that order of about 3'6". That's a creeper crane, weighs 600 tons. The jib and capable of lifting 122 tons. There are the buttress threaded screws to luft and the jib, which cross-travelled on a rack and pinion drive from one truss to the other one.
In addition to the main crane, there were also auxiliary hoists for lighter lifts and to assist in manoeuvring members into position. Mallard's shadow can be seen here as he films this scene, standing in a cage suspended from the crane.
That's Vic Whittleson, the crane driver and the creeper crane. He was on the maintenance for years too after the bridge was finished. There were telephonic communications with the crane drivers and everybody concerned with any particular operation. They were all interconnected by telephone. So the lifting cleats on most of the cord members, which went up to anything up to 150 tons, were so placed so that on lifting it assumed that approximately the right angle of slope that it would attain when fixed in position. As you can see, there were 4 webs and 2 separate half cords right throughout.
This is the last lower cord of the northern cantilever. The completed southern cantilever truss is on the right. Once the last bottom cord member was held in place, it was possible to step across the gap at the crown. Ennis, followed by Hipwell, made the first crossing of the harbour by foot rather than by ferry. This diagonal member forms the last triangulation at the crown of the arch. It was an essential stage prior to closing the arch. The arch members were brought from the workshops on a pontoon and lifted into position by the creeper crane.
That shows the hanging off of the cords just after it had been connected, and that shows the diagonal being lowered to complete the triangle prior to the erection of the post and the corresponding top cord section. You can see the lever, how tightly all these service bolts were tightened when it required a length of pipe on the end of the spanner and 2 men pulling on it to tighten them. That's due to the thickness of the plates. Certain of the plates were very thick, and they had a roller straight in the shock, but it didn't get all the buckles out of the. It was very ever so slight, of course, but they had to be absolutely tight in contact over the whole surface of contact.
All main cord members were assembled in pairs and are hollow. Access to the inside of the cord was through the manholes in each half member. During riveting, men inside would push the white-hot rivets through the holes and brace them for the riveter to form the head.
The riveting furnaces were oil-fired for the most part. They did have some coke with rivet forges, but for the most part they were oil-fired. The longest rivet in the bridge was 14 inches long and weighed about 7 pounds. And there were 690 tons of field rivets, let alone the shop one rivets. And there were about, the total number of rivets, they tell me, was about 5 million.
The manholes were later covered, but they still provide access for internal inspections.
That's the cage we used to go down onto the pontoon. We get a launch out from my workshops where my office was, and get on the pontoon. Most of the The contractors brought out a nucleus of workmen, tradesmen, particularly in for the fabrication and also on the erection. But the bulk of the working force were Australian. The majority of them were Australian. It wasn't without a certain amount of risk because the objects were always falling onto the pontoon, service bolts and nuts and things that you had to take the risk. It was always much safer once you felt much safer once on top. They did have a little cubicle with a 2-inch plate on the top, but no one ever went into it. It was bad for their morale. Oh, there were 17 unfortunate chaps killed, mostly from things falling on them. Very few actually lost their balance, but 1 or 2 did. And 1 or 2 killed in the shops, getting tangled up with the batteries of drills. They would stand up on the plates, and the cuffs of their trousers to get in the drill was. That shows the anchorage link connecting the cables to the extremity of the top cord. The cables were arranged in 8 rows of 16, 128 in all. Those are the hydraulic jacks. The sockets were picked up with 2 9-foot 3-inch diameter bolts, passing into a saddle over an 11-inch diameter pin in the link, and then continuing to house the hydraulic jack. And if they wanted to ease the nuts for running them out, as it was done in the lowering of the operations, the hydraulic pressure would be applied. That just eased the weight off the nuts, and they were able to unscrew them by hand. There was a gap of about 3 foot 7.5 inches at 72 degrees Fahrenheit at that stage before lowering operations commenced.
A temporary hinge arrangement was attached to the ends of the bottom cords, together with a tapered steel locating spike, which helped to align the 2 halves. When the ends of the cantilevers met, the temporary crown unit formed a structural hinge.
The lowering operations occupied 12 days and nights, working 2 12-hour continuous shifts. They commenced on about the 7th of August 1930 and finished on the 19th of August 1930. And there was such public interest manifest in these operations. The clothing was given out in the press that the bridge would be joined at 8:45 the following morning. That would be on the 20th of August, because that's the time that when all the ferry services converged on the quay, so that the greater majority of people would have an opportunity of witnessing the event. The closing of the arch actually took place at 10 p.m. the night before on the 19th, but the signal was, it was advertised that the operation would be indicated by the breaking of the Union Jack and the Australian flags at the tops of the jibs, the 2 creeper cranes at the centre. And when that, it was a very thrilling moment, because when that heard, everything that had a siren at the ships and anything that could make a noise made it. And it was a terrific din, but it was very thrilling actually. I was up on there with Mr. Hipwell and Mr. Martin, the shop superintendent at the time.
Joining the cantilevers changed the structure into a self-supporting 3-hinged arch. This was a temporary condition, allowing the bottom cord to take the thrust of the arch while the top cord was completed.
When the bridge became a three-hinged arch, there was a thrust of 40,000 tons on each of those bearings.
This post is the first of three members that closed the open triangle at the crown. Note the foreman using the telephone to the crane driver. This centre post maintains the depth of the arch truss at the top of the bridge by supporting the last top chord members. After the centre post was in place, the two top chord members completed the arch truss work.
That's the upper chord section being put up, and the numbering was the lower panel points were even numbers, and the upper panel points were numbered with odd numbers. Getting that, remember, the correct tilt, the auxiliary hoist was on is attached to one end of the cord, and the main lift is taken at the point of balance.
This was the scene at the top joint looking towards the south side of the arch. The inner half of the last top chord on the north side is held in place, ready for the temporary bolts at its end joints.
All the steel that it was specified, of course, all the steel that could be manufactured in Australia was supplied. There were about 23% steel, or 27% rather, of steel came from Australia. All the silicon steel, which is about 30% stronger in compression than ordinary carbon steel, came from Mr. Dormelong's works in Middlesbrough.
This is the arrangement at the crown of the arch prior to conversion to a two-hinge arch. After all arch members were in place and the top chord had been made continuous, the hinge could be removed and replaced by fixed plates, making the bottom chord continuous. The first step was to fill the gap in the top chord.
Now, in order to bring about the two-hinge condition, it was necessary to push back the extremity of the top chord some 5 inches. And for that purpose they had 4 960-ton hydraulic jacks working at about 4 tons per square inch hydraulic pressure. And the jacks were located on the flanges of the chords, one at the bottom flange and one at the top flange, and with the saddle and the pin in between them. So it was possible to push them back and then put packs in. It was calculated on the day the correct amount of jacking to be done, because it depended upon the load on the bridge at the time and also the temperature. They had some 40-odd thermometers all over the bridge in order to determine the temperature, and from that at the time on the day, it was they had to calculate the amount of jacking, and during that operation the crown of the lower chord at the lower chord joint rose 13 and a half inches up.
Manual jacks were also used as a safety measure to maintain the gap should the hydraulic jacks fail.
When the correct gap had been attained, they sent down a message to these packs were on the planing machine in the shop, and they were planed down to the necessary thickness at all speed and brought up to the job in the shortest possible time and put in. Then the jacks released back onto the packs, and then it became a two-hinged arch.
With both chords continuous and taking the thrust, the arch was now in its final two-hinge state.
Each of those cables would weighed about 8.5 tons and 1,200 feet long, and they were arranged in rows of 8 rows of 16 at the anchorage, and then before going into the ground they were into 32 rows of 4, And down in the anchorage tunnel at the lowest point was 130 feet below sea level. And down at that level they were in 64 rows of two. The hangar was laid horizontally in a cradle built of two railway stringer girder sets in tandem, with horns at each end to house the hangar. The hangar was 198 feet long, or no, 200 feet for that matter. And as it was lifted up, the auxiliary hoist turned it into the vertical position. And you'll notice when it's being lifted, this horn on this cradle allowed the top of the hangar to come up and make contact with the gussets underneath the cord, while the ropes hung down the side of the cord.
This view southwards from Milson's Point shows the arch complete, with both creeper cranes at the crown. The hangar is attached under the arch rib, and the cradle stands clear. Ennis and Bradfield worked well together and always attended important stages of construction.
You see the ropes from the crane are hanging down eccentrically from the axis of the hangar to allow it to come up underneath the bridge. That's lowering the lifting cradle from the hangar after it's been attached to the cord.
The project had its share of bad weather. In September 1930, this westerly gale was filmed by Mallard as he waited for a hangar to be erected. The wild conditions caused a postponement, and the pontoon was taken back to the loading bay in the workshop. But the first hangars were soon in place, ready for the decking.